Hello and welcome to the Connected and Autonomous Vehicles course. As part of the Learn Robotics program, this course will guide you on working with connected and autonomous vehicles. Let's review the course unit details. This course is designed to delve into the realms of computer vision and artificial intelligence within the framework of the Robot Operating System, ROS. This course unit equips you with the foundational knowledge and skills necessary for understanding and working with connected and autonomous vehicles, CAVs. You'll explore the core principles behind autonomous cars, delve into the Robot Operating System, ROS, a critical software framework for robotics, and gain hands-on experience implementing functionalities for autonomous navigation. The course is designed with the following aims in mind. Introduce the concept of autonomous vehicles and their potential impact on transportation. Equip you with a strong understanding of the Robot Operating System, ROS, for robotic development. Develop essential programming skills for building communication pathways within ROS networks. Explore key technologies for autonomous navigation, such as laser scan matching and simultaneous localization and mapping, SLAM. Provide hands-on experience in implementing basic autonomous behaviors through real-world projects. Upon successful completion of this course unit, you'll be able to explain the fundamental concepts of autonomous vehicles and their significance in modern transportation. Describe the core functionalities and applications of the Robot Operating System, ROS. Navigate the ROS file system and manage software components effectively. Utilize publisher and subscriber functionalities within the ROSP API to facilitate communication in ROS networks. Implement complex functionalities using services and launch files within the ROS framework. Explain how ROSP manages time synchronization and utilize bag files for data recording and playback. Apply laser scan matching techniques to enhance odometry accuracy for autonomous navigation. Grasp advanced concepts and applications of laser scan matching for robust odometry performance. Set up a robotic system for functioning and implement teleoperation for remote control. Design and implement a wall-following behavior using reactive methods in ROS. Master the concept of ROS transformations and frames for accurate coordinate handling within robotic systems. Explain the principles of simultaneous localization and mapping, SLAM, and its role in autonomous navigation. Implement a pure pursuit controller for autonomous path following and engage in research projects related to connected and autonomous vehicles. The syllabus is divided into two sections, lectures and labs, focusing on ROS, Robot Operating System, and its applications. The lectures include 14 topics, starting with an introduction to autonomous cars and ROS, progressing through key concepts like ROS file system, ROSP API, laser scan matching, and localization techniques such as SLAM. The Labs section complements the lectures with hands-on exercises, including tutorials on installing Ubuntu and ROS, working with tools like TurtleSim, ROS services, simulators, and transformations. The syllabus emphasizes a structured blend of theory and practical skills to develop expertise in autonomous systems and ROS applications. Here, the detailed course outline provides an in-depth structure for learning autonomous vehicles and ROS, Robot Operating System. It starts with the fundamentals of autonomous cars, the ROS framework, and its file system. The course focuses on the ROSP API for essential tasks like publishing, subscribing, services, and managing data with bag files. It delves into advanced topics like laser scan matching for odometry, teleoperation, and reactive methods such as wall following. Key concepts like ROS transformations, SLAM, simultaneous localization and mapping, and navigation algorithms like Follow the Gap are explored. The course concludes with a practical project on building a pure pursuit controller, enabling hands-on experience and research-oriented learning. The desired requirements include prerequisite courses, MT01 to MT08, familiarity with robotics concepts, and intermediate programming skills in Python and C++. Additionally, participants need specific software, such as Ubuntu/Raspberry Pi OS, ROS middleware, and OpenCV libraries, as well as hardware like Raspberry Pi, sensors, motors, and an internet-connected computing device. The recommended skills include ROS programming, machine learning, basic physics, calculus, and statistics, along with Unix/Linux command line knowledge for file handling, process management, and software installation. These requirements ensure a strong foundation for participants to engage effectively in the course. Introduction to autonomous cars. Autonomous driving levels, autonomous vehicles architecture, and sensors. Autonomous cars are vehicles equipped with advanced technologies that enable them to navigate and operate without human intervention. These technologies primarily rely on computer vision and artificial intelligence to interpret the surrounding environment, make decisions, and control the vehicle. The goal of autonomous cars is to enhance safety, efficiency, and convenience in transportation. Autonomous cars, also known as self-driving cars, are vehicles equipped with advanced technologies that enable them to operate without human intervention. The primary objective is to enhance transportation safety, efficiency, and convenience. Core technologies. Computer vision. Autonomous cars utilize computer vision systems to interpret the surrounding environment. Cameras capture visual data, enabling the vehicle to perceive and understand its surroundings. Artificial intelligence, AI. AI algorithms process data from sensors to make real-time decisions. Decision-making includes navigation, obstacle avoidance, and adherence to traffic rules. Autonomous driving. The 6 levels of autonomous driving. In L0, the driver performs all driving tasks. As we move up the levels, the vehicle takes on more responsibility, with L1 offering driver assistance features, L2 combining automated functions like acceleration and steering while requiring driver engagement, and L3 allowing conditional automation where the driver is not required to monitor the environment but must be ready to take control. L4 represents high automation, where the vehicle can handle all driving functions under certain conditions. And finally, L5 signifies full automation, where the vehicle can drive itself under all conditions, although the driver may have the option to take control. Important aspects while designing autonomous car. These include localization and mapping, which allows the vehicle to determine its precise location and create a map of its surroundings. Scene understanding involves the car interpreting its environment, recognizing objects, and predicting their movements. Trajectory planning and control encompass the vehicle's ability to plan and execute safe and efficient routes, including steering and acceleration. Finally, human interaction focuses on how the autonomous car communicates with passengers and other road users, ensuring a smooth and predictable driving experience. Benefits: increased safety through reduced human error, improved traffic flow and fuel efficiency, enhanced accessibility for individuals with mobility limitations. Challenges: ethical and regulatory considerations, integration with traditional, human-driven vehicles, addressing cybersecurity concerns to prevent hacking. Major technology and automotive companies such as Tesla, Waymo, and Uber are actively involved in developing and testing autonomous car technologies. The field continues to evolve rapidly, with ongoing research and advancements aimed at achieving widespread adoption of self-driving vehicles. Many companies are testing AVS, autonomous vehicles, e.g., Tesla, Ford, Waymo, Delphi. Understanding autonomous vehicles architecture. AV driving stack represents the different layers of technology involved in autonomous vehicle, AV development. Key components. Tech stack. This refers to the software and hardware components that make up the AV system. It includes application, the top layer, responsible for high-level tasks like route planning and decision-making. Driving assistance software handles functions like adaptive cruise control and lane keeping. Sensor fusion combines data from various sensors, radar, LiDAR, camera, to create a comprehensive understanding of the environment. Mapping creates and updates maps of the driving environment. Compute, the processing power, CPUs, GPUs, needed to handle the complex calculations involved in AV operation. Sensors, devices that collect data about the vehicle's surroundings. Automated driving stack, Delphi and partners. This section highlights the specific technologies and partners involved in Delphi's AV development efforts. It includes Automatica, a company specializing in autonomous driving software. Here, a mapping and location data provider. Intel provides high-performance computing hardware. Quanergy, a supplier of LiDAR sensors. Overall, the AV driving stack illustrates the complex interplay of hardware, software, and data that is necessary for the development of safe and reliable autonomous vehicles. Ford Fusion is equipped with various sensors and cameras for autonomous driving development. These sensors are crucial for the car to perceive its environment and make driving decisions. Advantages of using more sensors. Better environment data. More sensors can provide a more comprehensive and accurate picture of the surrounding environment. Increased sensor redundancy. Redundancy can improve reliability and safety by providing backups if one sensor fails. Disadvantages of using more sensors. Decreased costs per vehicle. Fewer sensors can reduce the overall cost of manufacturing and maintaining the vehicle. More electric vehicle range. Fewer sensors can reduce the power consumption of the vehicle, leading to increased range for electric vehicles. Here we can see sensor placement on Tesla and Ford autonomous vehicles. Here's a breakdown of the sensors used. Tesla. Camera. 8 cameras. Radar. 1 long-range radar. Sonar. 12 sonar sensors. Ford. Camera. 7 cameras. LiDAR. 2 LiDAR sensors. LR radar. 2 long-range radar sensors. SR radar. 4 short-range radar sensors. Sonar. 10 sonar sensors. Key differences. Tesla relies heavily on cameras. Tesla uses more cameras than Ford, likely due to its reliance on vision-based autopilot system. Ford uses LiDAR. Ford incorporates LiDAR, which provides more accurate depth perception and is considered a key technology for autonomous driving. Ford has more radar sensors. Ford uses more radar sensors than Tesla, which may provide better coverage and redundancy. Overall, both Tesla and Ford use a variety of sensors to achieve a comprehensive understanding of their surroundings, enabling them to navigate safely and efficiently. Tesla Model Y. A camera is mounted above the rear license plate. Ultrasonic sensors, if equipped, are located in the front and rear bumpers. A camera is mounted in each door pillar. 3 cameras are mounted to the windshield above the rear view mirror. A camera is mounted to each front fender. Radar, if equipped, is mounted behind the front bumper. Model Y is also equipped with high-precision electronically assisted braking and steering systems. Different types of sensors. Camera. Cameras are the most widely used sensors in autonomous vehicles. They provide high-resolution images of the surrounding environment, which can be used to identify objects such as other vehicles, pedestrians, road signs, and traffic lights. Cameras can also be used to track the movement of objects over time, which is essential for autonomous driving. Radar. Radar sensors emit radio waves and measure the time it takes for the waves to reflect off of objects in the environment. This information can be used to determine the distance and speed of objects. Radar sensors are not affected by lighting conditions or weather, which makes them a valuable addition to autonomous vehicles. LR radar. LR radar stands for long-range radar. LR radar sensors have a longer range than traditional radar sensors, allowing them to detect objects at greater distances. This makes them ideal for highway driving and other situations where vehicles need to be able to see far ahead. SR radar. SR radar stands for short-range radar. SR radar sensors have a shorter range than traditional radar sensors, but they have better resolution. This makes them ideal for detecting objects in close proximity to the vehicle, such as pedestrians and other vehicles. LiDAR. LiDAR sensors emit laser light and measure the time it takes for the light to reflect off of objects in the environment. This information can be used to create a 3D map of the surrounding environment. LiDAR sensors are very accurate and can detect objects at long distances. However, they can be expensive and are not as effective in low-light conditions. Sonar. Sonar sensors emit sound waves and measure the time it takes for the waves to reflect off of objects in the environment. This information can be used to determine the distance and speed of objects. Sonar sensors are not as accurate as radar or LiDAR sensors, but they are very inexpensive and can be used in a variety of conditions. Autonomous vehicles use a combination of sensors to create a complete picture of their surroundings. Cameras are used to identify objects, radar is used to measure the distance and speed of objects, and LiDAR is used to create a 3D map of the environment. LR radar and SR radar are used for long-range and short-range detection, respectively. Sonar is used to detect objects in close proximity to the vehicle. By combining the data from all of these sensors, autonomous vehicles are able to build a detailed and accurate understanding of their surroundings. This information is then used to make decisions about how to navigate safely and efficiently. For example, an autonomous vehicle might use the data from its cameras to identify a pedestrian crossing the street. The vehicle would then use its radar and LiDAR sensors to measure the distance and speed of the pedestrian. This information would be used to determine if the vehicle needs to slow down or stop to avoid hitting the pedestrian. Autonomous vehicles are still under development, but the sensors described above are essential for their safe and reliable operation. As these sensors continue to improve and become more affordable, autonomous vehicles will become more and more common on our roads. Various sensors and technologies are used in advanced driver assistance systems, ADAS. These systems are designed to enhance safety and comfort for drivers. Here are some of the key features highlighted in the diagram. Sensors. Long-range radar detects objects at a distance, enabling features like adaptive cruise control and collision avoidance. Short/medium-range radar, used for features like blind spot detection and rear cross-traffic alert. LiDAR provides precise distance measurements, essential for functions like autonomous emergency braking. Cameras capture visual information for lane departure warning, traffic sign recognition, and pedestrian detection. Ultrasound, used for parking assistance features like park assist and rear collision warning. ADAS features. Adaptive cruise control maintains a safe following distance from the vehicle ahead. Lane departure warning alerts the driver if they unintentionally drift out of their lane. Blind spot detection warns the driver of vehicles in their blind spot. Rear cross-traffic alert detects vehicles approaching from behind when reversing. Park assist helps the driver park the vehicle by providing guidance and control. Emergency braking automatically applies the brakes to avoid a collision. Overall, the diagram demonstrates how a combination of sensors and technologies work together to provide drivers with valuable assistance and enhance road safety. Here is a list of sensors commonly used in autonomous vehicles, along with their key characteristics and applications. Cameras are the most prevalent, offering a visual understanding of the environment. LiDAR uses lasers to create a 3D map, crucial for accurate perception. Radar uses radio waves for object detection and adaptive cruise control. Sonar and ultrasonic sensors are used for short-range tasks like parking assistance. Each sensor type has strengths and limitations, and autonomous vehicles often combine multiple sensors for optimal performance and redundancy. Autonomous vehicles leverage a variety of sensors to gather comprehensive information about their surroundings. Each sensor type has specific strengths and limitations, and combining them enhances overall perception and reliability. The sensors enable various features like object detection, localization, navigation, and driving assistance. Let's discuss the high-level software architecture of autonomous vehicles. It highlights the complex interplay of various components in an AV system. Accurate perception, robust planning, and precise control are crucial for safe and reliable autonomous driving. Simulation plays an important role in testing and validating the system before real-world deployment. Here's a breakdown of the key components and their interactions. 1. Sensors. Environment. Collects data about the vehicle's surroundings using various sensors like cameras, LiDAR, radar, and others. Self. Collects data about the vehicle itself using sensors like IMU, GPS/GNSS, and odometer. 2. External perception. Combines data from environment and self-sensors to create a comprehensive understanding of the vehicle's surroundings and its position within it. 3. Localization. Determines the precise location of the vehicle within the environment using data from external perception, GPS/GNSS, and odometer. 4. Planning. Global. High-level route planning based on the destination and traffic conditions. Behavioral prediction. Predicts the behavior of other vehicles and pedestrians in the environment. Local. Low-level planning for immediate maneuvers like lane changes and turns. 5. Control. Generates commands for the vehicle's actuators, e.g., steering, brakes, throttle, to execute the planned maneuvers. 6. Actuation. Carries out the control commands to move the vehicle as planned. 7. Mapping database. Stores information about the environment, including roads, traffic signs, and other relevant features. 8. Simulation. Used for testing and validating the AV's software and hardware in a virtual environment. 9. Outcomes. Represents the final result of the AV's actions, such as reaching the destination safely and efficiently.